Okay, so in yesterday's lecture, we basically looked at how we can set up two-dimensional partial differential equation or two-dimensional finite difference method to solve two-dimensional partial differential equation. Give me 1 minute. I lost my stuff. Where is it? There you go. All right. So in that particular lecture, I showed you guys how you can derive the Crank-Nicholson scheme to solve a two-dimensional heat equation. But in reality, whatever you learn is not limited only to Crank-Nicholson. Okay. The reason why I choose Crank-Nicholson is because I believe that if you can do it for Crank-Nicholson scheme, you can easily do it for the BTCS scheme and of course the FTCS scheme. Okay. So for me, maybe just open up a few slides here. So for the BTCS, Crank-Nicholson scheme that we covered yesterday, you have dt d time is equals to alpha of this. So the difference with what we have is actually the introduction of an additional spatial derivative because we are dealing with a two-dimensional problem. Okay, and you'll realize if you go out and work in the future, if you're going to do research, you'll realize that a lot of the problems that we solve cannot be done in 1D, or in fact, it cannot also be done in 2D because our world revolves around a three-dimensional axis. Okay, so two-dimensional itself is already a representation of what we can do. But of course, if you're going to extend this to three-dimension, it is going to be more complicated than this. Okay, so for this, we actually use the Crank-Nicholson scheme to solve it, in which case you have Tjk at time level n plus 1 minus Tjk at time level n divided by delta t. And on the right-hand side, you have the central difference scheme for both of your spatial derivative. Okay, and because it's a Crank-Nicholson scheme, we actually take the average of it. And what you guys learn from there is from this central difference scheme, you will find that you basically get a stencil of 5 points. So every time your equation is applied, it involves 5 points, and those 5 points are basically this stencil that you see here. The middle point is always our point of interest, so that is our J and K. So just a reminder to everyone, when we write J or when we write our variable in finite difference method for 2D, the space derivative or the spatial points, we refer it to the subscript. So J represents the X point, K represents the Y point, and the superscript is used as your time level. Okay, so just to remind everyone, if you're going to solve a question on 2D FDM in your final exam or final assessment, please use the notation or the convention that we have defined in class. A lot of you guys in exam will probably write it, even if I give you a one-dimensional problem like this, okay, and I ask you to write the FTCS scheme, you are going to write it as Qjk plus 1 minus Qjk over delta t by taking t as the time. So let me remind everyone, please stick to the convention that we have, okay? So in our stencil, we have jk, then you have j plus 1k, j minus 1k, here will be jk minus 1, and jk plus 1, all right? I've shown you guys how to actually collocate it. The collocation is very straightforward. You apply it at every point, and then you just sub in the index for jk and n. Effectively, how many points you have that are unknown would give you the same number of matrix that you have, meaning that if you have 9 points, you'll get 9 equations. If you do everything correctly, you will have 9 unknowns that correspond to the unknown points in your problem that you have, okay? I also showed you guys that to actually set up the equation is going to be tedious. So an easier way is just to write it in a system matrix form. So that system matrix form is shown to you in this equation here. Primarily what we have is we have an identity matrix, and then we also have a Laplacian matrix, okay? And you will see that a lot of the two-dimensional problem that we have, usually they involve some form of this equation here. I'm not saying all of them. I'll say the majority of them involve some form of a term like this. For example, you have d squared t dx squared plus d squared t dy squared. And this effectively comes from your Laplacian of del squared t. Okay, so you'll see that a lot of the partial differential equation, a lot of the engineering problems that you're going to solve involve some form like this. Okay, For example, if you talk about the wave equation in 2 dimension, you will have d square u again dx square plus d square u dy square. You can see the only thing that is different is actually the variable, but the spatial derivative is the same. Okay, so because of that, we can introduce a Laplacian matrix. And I've shown you guys ultimately what we are doing when we set up the Laplacian is basically just apply the stencil at every point, figure which one is the boundary condition, which we are not going to, we're going to move it to the right hand side. That will account it later. And we will see which are the coefficient in front of the unknown that we have. Okay. So those are the concepts that I have outlined in yesterday's lecture. I hope you guys took some time to basically revise on it, because today we want to see how we can implement this from a Matlab point of view. Okay, to make things simple, let's say again we have a 2-dimensional problem where the distance or your 2-dimensional domain is basically a rectangular plate, where in the x direction it has a width of Lx. Okay, and in the y direction you have a width of Ly. So you have 4 boundary conditions given to you. You have F1, F2, F3, and F4. So F1, F2, F3, and F4 can be values. So this, for example, can be 0, can be 1, can be 2, or they can be functions as well. So for example, this can be x plus 1, meaning that at every different point x, you will have a different value of f. So the same goes for this. It can be a function of y, for example. So as y increases, the boundary condition also changes. Okay. So you also have an initial condition. The temperature everywhere in the point xy in your domain here at time equals to 0 if is given by a value or a function. Okay, so you're asked to discretize this using delta x, delta y, and delta t. I'm not going to show all the derivation again. The whole point of this lecture is to go through the Matlab part. Okay, I suppose everything is clear about what we are trying to do now before I move on.
Sir,
Yes.
may I ask what's the general arrangement for the boundary condition column vector? Like, are we starting from the left-hand side first, and then we go to the right, and then bottom, and then to the top?
It doesn't matter actually. I'll show you later. But as long as you are consistent, then it is okay. Because the boundary condition in the end, it's when, for example, if you're at the first point where you have 2 boundary condition like this, when you have a stencil like this, you have 2 boundary condition. You're going to move them to the right hand side, and remember, everything on the right hand side is their known values. So this might look very lengthy, but if you sum up this or you write this in very simple term, effectively you have a matrix A times your column vector T is equals to a right hand side B. So to find your T is just the inverse of A times B. So all the boundary condition for each row, you are going to sum it up into your column vector here. So this might not be clear at this moment, but let me go through the Matlab code. Hopefully that will be clearer to you guys.
Okay.
All right. Okay, so let's say we have this problem, like I've said before, you have all this problem with boundary condition and initial condition here. Okay, so as with all finite difference method, whether it's 1D, 2D, or 3D, the first thing is to set up your grid points. Okay, so let's say we set up our grid point like this. You have your grid points on the boundary. You guys can see the dot, right, when I'm moving in like this. Do you? I'm sure you do. Okay, you can, yes, all right. You can see the grid points around the boundary here. So those points would basically be known from the boundary condition because they are points at the boundary. And then you also have all these interior points, those points in red. So these basically are interior points. And if you're given this problem here where all the values of T are given at the exterior boundary, it means that the only points with unknown temperature is the interior point. Okay, now one thing I want to make clear here is because I'm showing this from a Matlab implementation point of view, my index for J and K starts from 1 because Matlab cannot take an index of 0. Okay, which is why you see the first point is basically J1 and K1, second point J2 and K1, and so on. Okay, so I'm using a Matlab notation here, meaning that my J and K will always start from 1. So right now, in order for us to set up this grid point, it is very easy to use the function linspace in Matlab, because we are assuming that delta x is going to be uniform, meaning that delta x is going to be the same everywhere. Okay, and delta y is also going to be the same. So you can have two linspace function that will distribute your points in both x and y. So this linspace function will actually give you two row vectors. Okay, for example, if you call x, let's say I call xg, which is my grid point, I will have linspace, for example, let's say from 0 to lx, and I want to have, let's say, 100 points. Okay, then I'll have yg, you have the linspace command 0 to ly, and then you have 100 points. So this will give you two row vectors. The first row vector will give you all the coordinates, all the 100 points in the x direction. The second one will give you all the y coordinates in the y direction. Okay, so for each of these, you can have your nx and your ny. So nx is the number of points in x, ny is the number of points in y. You do not necessarily have to have nx to be equals to ny. Okay, the number of points you distribute in x direction can be different from the number of points you choose in the y direction. So there's no requirement for nx to be equals to ny. So that is one thing. The second thing is when you use the linspace function, all whatever points that you have in this linspace function will include the points at the boundary. So when you set up from 0 to lx over 100, this will be the first point, this will be the last point. So in your row vector, it will always take into account the endpoints in your x domain and your y domain. Okay, so that is the first step that you do. That is straightforward. Okay, now in the second step, if you recall from yesterday's lecture, let me get a new slide. If you recall in yesterday's lecture, if for example, if this is your grid points like this, let's say you have 6 unknowns in the center, you want to orient this such that when you write your column vector, it is written in terms of the 6 unknown points that you have over here. Okay, so these 6 unknown points, for example, if I follow my Matlab notation, it's a bit messy, give me one second. Now, if I follow my Matlab notation, you can see that the first unknown point, this red point right here, this is basically your first unknown point, and the index for j and k is basically 2 and 2. The second one, you have 3 and 2, 4 and 2. So for this, you will have 2, 3, 3, 3, 4, 3, and 5, 3, and so on. Okay, so we don't want to write it in terms of a matrix, meaning that we don't want to write it in terms of j and k, because when we orientate this into a column vector of unknown values, we want to number it such that it becomes a just a sequence or a series. So instead of jk, we just call this the first unknown, second, third, fourth, fifth, and sixth. We just call it by number. Okay, so from here you can see if this is 2, 2, 3, 2, 4, 2, and so on, we're going to rename these 8 unknowns into 1, 2, 3, 4, 5, 6, 7, and 8. Okay, but the question is we need to reorder the numbering. Okay, so that for each value of j, for each value of k, you will get the corresponding node numbering from 1 to 8. Okay, so what I mean by that is this. So, I hope you are following. So let's say this is J1, K1. Okay, this will be a J2, K2, J3, K3, J4, K4, and let's say you have J equals to 5, K equals to 5. Okay, and then you have the second point where this would now be K equals to 2. So this would be J2, K2, J3, K3, J4, K4. So the reason why there's a need to reorder the number is because when you call your xg, okay, your xg is a row vector that is one row multiplied by nx points. Okay, if we use this example here, you have 5 points. So basically xg, when you call your linspace, it becomes a row vector of 5 points. So it has a size of 1 by 5. The same goes for your YG. Let's say you have until k equals to 5. So your YG will basically be a row vector that has a size of 1 to 5. Okay, so it only has one row, but we use this index here. For example, you have an index of 1, 2, 3, 4, and 5. So each of these, let's say this is for J and this is for K. Each of these J will give you 1 point in X. Each of these K will give you 1 point in Y. But we know that for J equals to 2 and K equals to 2, this will correspond to unknown T1, because as I've said earlier, if you recall from the earliest, what I've written here earlier, this is 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, and 6 correspond to the row in our column vector. Are you guys following? Those 1, 2, 3, 4, and 4, 5, and 6 correspond to my T1, T2, T3, T4, T5, and T6. But T1, okay, T1 is basically my T22 in my grid form. So I need to be able to convert J equals to 2 and K equals to 2 into 1. The same thing, I need to be able to convert J3, K2 to be the second unknown, or row number 2 in my column vector here. Okay, so J equals to 4, K equals to 2 would need to correspond to T3, the third unknown in my column vector. Is this clear, or do you need me to repeat this?
Repeat.
A bit clear, a bit unclear. Okay. You recall towards the end of yesterday's lecture, I told you guys you can write it in system matrix, correct? So I said, okay, you have a column vector T. Oh, sorry, not column vector. What was the thing again? We stated that we wanted to write our TJK into a column vector of T. Okay, but this column vector of T will not take into account the boundary condition, because everything on the boundary condition, we're going to move it to the right hand side. Okay, so when you want to write it as a column vector, the numbering in a column, because you cannot think of this from an algorithm point of view, you have to think of this from a Matlab point of view. This whole thing is about how you implement it in Matlab. And to implement it in Matlab, you need to understand why there's a need for the node numbering, because when you try to write this as a column vector, this becomes one column, but with multiple rows. Each row corresponds to each unknown that you have. So in this example, I have numbered my row or my unknown in terms of 1, 2, 3, 4, 5, 6 like this. You can also number it 1, 2, 3, 4, 5, 6 if you want. If you do that, then the numbering system, which I'm going to show later, is going to be different. But the order of numbering depends on you, or it depends on what the question wants you to do. For this example, just to illustrate, I have assumed that 2, 2 correspond to the unknown number 1. 3, 2 correspond to unknown number 2. 2, 2 correspond to unknown number 1, 3, 2 number 2, and J2, K2 correspond to unknown number 3, and so on. Okay. What's covered, which means we can write whatever equation we want as long as we are able to satisfy the condition. Yes. So there's this question in the chat box if you guys are not paying attention. Basically, you can write any equation as long as you can convert when J is equals to 2 and K equals to 2, you basically need a function. Okay. For J equals to 2, K equals to 2, you basically need a function that will equate, you need a function that takes in J and K such that it will give you a value of 1 in this case, sorry, 1 because it's the first unknown. When you have J equals to 3 equals to 3, you need to write a function, the function will probably be the same. Okay, you need to write one function such that whatever index J and K that you give, it will give you this distribution that you have. Okay, so I'm going to show you the function later, but I want you to, the point of asking you all of this or telling you all this is so that you understand why there is a need to write it in this form. We write it in this form because in Matlab, this becomes a column vector. So you don't have your j and k anymore. You don't, when you call it, if this is your t, right, your column vector, you call it as t1, which correspond to the first row. T2 will correspond to the second value. In a column vector, you are not going to write 3, 2, for example, because it's a column vector, it's not an array. Okay, so I hope you understand why there is a need to write it in terms of a column vector. Okay, so if you need to absorb it, then you just try to accept as much as you can, and hopefully you can do the revision later. But assuming that you understand why there's a need to write it or reorder the numbering, what is then, the question then is, what is the function that you should write for f? So I'm just going to show it to you. The function that you can write for f is basically given by this equation here. Okay, so what is in? In is basically the node number corresponding to your column vector. It is basically this value that we want. Okay, so let me just reproduce that. So in, again, you can call it whatever you want, is right now written as, you can see you have j minus 1 plus k minus 2 and x minus 2. Okay, so you have j minus 1 plus k minus 2 times nx minus 2. So I'm going to explain why is it that we use this equation. But for now, let's just, if this is the function that we want, this is our function f. What happens if j is equals to 2 and k equals to 2? When j is equals to 2 and k equals to 2, what happens to our in? Our in becomes 2 minus 1 plus 2 minus 2 times nx. In our case, nx is equals to 5. Okay, so you have 5 minus 2. So this becomes 1, which is what we want here, because at j equals to 2 and k equals to 2, it corresponds to the first unknown, which we are going to call it t1, or the first unknown in our column vector. What happens if j is equals to 3 and k is equals to 2? When j is 3 and k is 2, we understand that, sorry, all this is j, k1, no one. So, sorry, this, yeah, k2, 3, 4, 5 is here. This is still all k1 for the first point. Okay, so for j3, k2, we know that we are referring to this point, the second value. So what happens to our in? Again, substitute j3 and k2 here. You're going to get 3 minus 1 plus 2 minus 2 times 5 minus 2. So this becomes 2, which is what we want. It's the second value. It's the second grid point that we have. Okay, so you can substitute in all the values of j and k, or the 6 values of j and k, and you'll find that corresponding values of in will correspond to 1, 2, 3, 4, 5, and 6. And the reason for that is because of the way we are writing this. We know that we don't want the 2 endpoints because the 2 endpoints do not contribute to your column vector of unknown. Okay, and we know that okay, if you look at this equation, you have this nx minus 2. The reason for the 2 is because we don't want to account for, sorry, we don't want to account for the 2 endpoints over here because they don't contribute to it. And then you have k minus 2 times nx minus 2. So what is the reason for this k minus 2? Because every time we want to move up to this, okay, we have already increased the numbering by 3. For example, if we have one more here, okay, 1, 2, 3, 4, 5, 6, this will be 7, 8, and 9. So every time we finish one row of j, the numbering would have increased by 3. So in the first case, when k is equals to 2, you can see that this entire thing here is going to be 0. Okay, but when this k increases to 3, when k increases to 3, what happened? One second. When k increases to 3, let's say j equals to 2 and k is equals to 3. When j is 2 and k is 3, what happens to in? In becomes 2 minus 1 plus. So here is k is 3, you have 3 minus 2 times 5 minus 2. So again, the reason for this is so that we get 3. And here, right now, you have k minus 2 because you have 1. So after completing one row, after completing one k row, the number should have increased by 3 already. So you can see here, these will always repeat from J1 to J3, it will be always increasing 1, 2, and 3. The addition here would be whatever you have added after every row. So after k is equals to 2, you would have 1 times 3, which is 3. So the first point in k equals to 3 would be 4. And then if you increase j equals to 3, k equals to 3, you'll find that in is equals to 5 and so on. And if you move one more ahead, you'll find that this becomes 2 times 3, which is 6, because you have already added 2 rows. Is that clear? It's basically just an ordering of your number. Perhaps I'm making it more complicated than it is, but if you get what is going on, it shouldn't be that difficult to understand. Do you have any questions? Okay. Do we need to do this when we denote the numbering by ourselves? What do you mean?
I mean, we can straight away see from the figure and then denote the numbering by ourselves.
Well, that
So
if you have 6, that is okay. But what if you have 3,000 points or 3,000 unknowns?
Oh, I see.
Yeah. So yes, when you look at this, yes, it's easy. It's 6 points, but rarely we have 6 points. When you do Matlab, you're supposed to do like what, 100 points, 1,000 points. So it becomes very difficult. Okay. That's the other this other question, just to confirm. 1, 2, 3 is referring to T1, T2, T3. 1, 2, 3 is referring to the first unknown, second unknown, and third unknown over here. T1, T2, T3 refers to T22, T32, T33, and so on. Yeah, T21, T31, and T41, and so on. It's basically referring from T.22 to 0.1, 0.32 to 0.2. So the purpose of this numbering is so that we can convert the grid points J and K into 1 and 2. Why do we actually need this? Because when you want to code it, when you want to set up your code to basically run, when you want to write your code to set up the Laplacian matrix, you are going to loop from, for example, from k equals to something for j equals to something. So this is the loop for the number of y points that you have. This is going to be the loop for the x points that you have. So the j and k that you are looping in your for loop is actually corresponding to the number of points in x and the number of points in y. You need to be able to convert this into this numbering system so that you can allocate it to the proper row in your Laplacian matrix. Remember what I did in class yesterday. I told you I have a Laplacian matrix that is multiplied to your column vector of unknown. In our example, we have a total of 9. So you need to be able to convert for the first, when you apply the stencil at the first point, j and k, when you apply it at this first point, yes, you know first point correspond to first row. But if you have 1,000 points, it becomes very difficult to keep track. So that is why we use that numbering system, that particular formula, such that for particular j and k, we know where it is in our matrix here. This matrix, okay, this coefficient matrix is not the same as this coordinate matrix. This is what students always misunderstand. They think that the matrix that you set up in your Laplacian, whatever row, whatever column, for example, row 3, column 3. Row 3, column 3 is basically 3, 3, correct, in your matrix. They will think that row 3, column 3 correspond to J3 and K3. That is not the same, because your column matrix, your matrix here, the grid is referring to the points that you have. If you have 8 unknowns, then you have an 8 by 8 matrix. Okay, so row 3, column 3 in this equation is not the same as J3, K3 in your coordinate matrix. So don't misunderstand that. Students get it wrong here because they misunderstand the grid points or the coordinate system in your grid to the matrix numbering system. Are we clear on that? Okay. Now, okay, let me do it this way. So the example or the equation that I've shown you earlier, i.e. in is equals to j minus 1 plus k minus 2 and x minus 2. This, again, I'm going to repeat, and this is important. This is not uniform. This is not universal. Okay. This is applicable for the way I rearrange my node like this. Okay. This is for the case where I don't want to account for the two boundary points. Now, if I give you another example, let's say again your two-dimensional domain of x and y. So we use the same thing. You have a total of 8 unknowns here. Okay. So instead of doing 1, 2, 3 horizontally, I do 1, 2, 3, 4, 5, 6, and 7, 8. I want to reorder my node number like this. It is okay. As long as you are consistent, it is okay. But the equation that you're going to use is going to be different anymore. It's going to be different now because the numbering system does not apply to this particular equation that you see. This is only for this numbering system. This numbering system is going to be different. So for this numbering system, how would you write your IN? You can see right now, we know that this is our J, and we know that this is our increasing K. So you see, we are actually increasing in Y first before we come in K. You swap your J and K term in the equation, well, to a certain degree. So in this case, because you're increasing in K first, you need to have K minus 1 so that this keeps looping around. And then here you have J minus 2 if, again, you don't want to account for the boundary points, okay? And instead of nx, it becomes ny minus 2 because there's no criteria that says nx has to be the same as ny. So if you want to do it this way, you can see the equation right now is different. So my point here is not to memorize this equation, nor is it to memorize this equation. What you need to do is understand the fundamental. Okay, this is what I keep stressing every time. If you understand what is going on, whatever question we give to you, you can solve it. Okay, but if you learn this unit by memorizing stuff and not understanding what is going on, you will think that you understand. You go to the final exam, you do it, you score very poor, and then you think, but I thought I understood what was going on. No, you memorize what is going on, but you don't understand the application of it. Okay, so in this case, I've said a few times already, whatever node numbering function that you come up with depends on how you want to orientate it, if you're doing it yourself, or it depends on what the question wants you to do. If the question says renumber your question this way, then you have to figure out what is the proper system. Okay, and in lab, I cannot remember if this lab 6 has something like this. But in exam, for example, we will obviously give you an indication of what numbering system we want, because if you don't do that, students will come up with their own numbering system, then the marking becomes very difficult. So understand the problem rather than memorizing the equation. Okay, so first step, set up your grid points, use your linspace and all of that so that you get your J and K index. Second step, create this function. So this can be written as a function handle, for example, in Matlab. Okay, or you can write a Matlab function file, which will become a very short Matlab function file that basically just states this mathematical equation. Okay, so that is your second step. In your third step, you will then have to run your loop so that you can set up your matrix. So I have partially shown what this is already. So to run this loop, you basically need two for loop. Okay, you need a for loop that loops over k. So let's say for k from 1 to okay, you cannot loop it from 1 to ny. you need to loop it over the number of points that you want to collocate. So let's say I have reduced it from 8 unknowns here to 6 unknowns to make it simpler. You cannot apply from 1 to an x or 1 to ny. The reason for that is because you loop it to the point where you want to apply your stencil. So you apply your stencil in our example here to these 5 points. So the first point that you're going to apply to be will be the middle point. Okay, so the middle point here, your j starts from 2. The last point in j will be 4. So it is effectively an x minus 2. Okay, so the same goes for your k. So when you write it this way, you are going to loop it from 2 to ny minus 2, and then you're going to loop it from from 2 to nx minus 2. Okay, so once you have this 2 loop, what is the first thing you need to do? You need to reorder your numbering system. So you have j minus 1 plus k minus 2 times nx minus 2 if we are using this numbering system. Okay, so once you have this, what does this tell you? This basically tells you where to place uh, the coefficients in the L matrix. Okay, because whatever in that you have, if in is equals to 3, we are referring to row number 3. If you calculate in is equals to 6, it refers to this. So if you have something as generic as this, even if you have 1000 points, if this is done correctly, you can place the points or the coefficients at where it needs to be. Okay. All right. So once you have this, you know where to place it. The question then is, how do you set up your Laplacian matrix? So of course, for this, you have your LIN. What is LIN? This is your main diagonal term. Okay. Give me 1 second. All right. Sorry about that. Okay. So in your Laplacian, as what I've said yesterday, it basically in Cartesian coordinate, it involves these 2 terms. Okay. So in these 2 terms over here, you can see it. There are 5 points. You have a j and k. You have j plus 1k, j minus 1k, jk plus 1, and jk minus 1. So there are 5 points. So when you set up your matrix, the matrix will follow something similar. Okay. So if you already know where you are going to place it in your matrix. So what you need to do is at whatever point that you collocate for that particular j and k, for a given j and k from your loop, you need to check whether that stencil has any boundary points or not. Okay, so rather than writing this first, maybe I'll show it. Wherever place you place your j and k, okay, you need to have some Matlab statement that checks whether at this particular stencil, are any of the 4 points surrounding it going to be a boundary condition or not? Because if it's a boundary condition, you don't have to worry about it. If it's not a boundary condition, then you need to calculate and place the thing correctly. We know that the point jk will correspond to the main diagonal because your j and k will always give you the main diagonal, correct? It is always your middle point. It is always this point over here. Okay. So how do you check if any of the boundary here belongs to a boundary on the left-hand side, on the right-hand side, at the bottom, or at the top? You need to have basically an if statement. Okay, so your 2 for loops will loop over all the number of points that you have. This will tell you where to place it. Next, you need to have an if statement. Okay, so I'm going to show you an example how we can actually do it. So let's say we want to determine if the point on the left, okay, if this is your point jk, we want to determine if the point on the left is going to be a boundary condition or not. Okay, so we use an if statement. So what we're going to say is if j is going to be greater than 2. So if j is greater than 2, what does it mean? If j is greater than 2, it means that when you apply your stencil, you're not going to apply your stencil at this point. Because when you apply a stencil at this point, you're referring to j is equals to 2, correct? So if you write a statement, if j is greater than 2, what this means is that if j is greater than 2, what does it mean? It means you're placing a stencil at all the points where j is going to be greater than 2. So this is j. So you're going to place a stencil at j equals to 3, and you're going to place a stencil at j equals to 4. Okay, so if j is equals to 3 and j is equals to 4, you know that the point on the left will never be a boundary condition because your grid point will look like this. It is only when you place it at j equals to 2, then one of the point becomes the boundary condition, correct? Okay, so if j is equals to 2, the only thing we know from here is that point on left hand side is not a boundary point. Okay, so every time when j is greater than 2, it means that the point on the left is not a boundary point. So if the point on the left is not a boundary point, then we have to take it into account into our Laplacian matrix. Okay, so in our Laplacian matrix, we need to incorporate this point, which is our j minus 1k. So j minus 1k, the coefficient will be 1 over delta x squared. So somewhere up there, you can define, for example, dx, I don't know, or let me call it dx coefficient is 1 over dx squared. Okay, so if your j is greater than 2, all the left-hand side point is not going to be a boundary point. So the question now is, how do you place it into your matrix? Remember, you have your column vector like this. When j is and k is equals to this, you have this function here that will tell you where is the main diagonal. But right now, you want to know where is this point. You want to know where to place this particular coefficient in your matrix here. You can again use this particular function. Okay, so this, as I've said earlier, you can write it as a function handle in terms of j and k. Okay, so if j is greater than 2, in order to know where to place it, you can say, okay, I at left hand side is basically this function. Let me rewrite. Let me see how to. Okay, let's say you have a function which I'll call, let's say I call it the in function. So in function is a function handle that takes in j and k, and this will have an expression of j minus 1 plus, sorry, j minus 2, k minus 2, and x minus 2. Okay, so this in is now your function handle name. So when j is greater than 2, the point on the left hand side is not a boundary point, so there is contribution in your Laplacian matrix. Okay, so what you do is you're going to call your the I that you want at the left hand side is basically given by in. Okay, so what should be the input in your function handle here? Anyone? So that I can understand whether you're following or not. What are we? Okay, in case you're wondering what I'm trying to say, what I'm trying to say here is whenever you apply your stencil, give me a minute, let me open the slides from yesterday. Okay, so this is the slides from yesterday. All right. Whenever you apply your stencil, some of the points are going to be boundary points, okay? And some of the points are not going to be boundary points. If you write your matrix like this, then it becomes easy for you to say that, okay, T11 is basically my first point, so the coefficient is basically alpha, okay? T21 is basically my second point, so coefficient is 1 over delta x squared, we have it here. And then you have T31, which is not there, it becomes 0. So mathematically, when you do it like this, you can see it. But here, the problem right now is for a given point j and k, okay, if I write an if statement that says if j is greater than 2, it means that the point on the left-hand side is not a boundary point. If the point on the left-hand side is not a boundary point, it means that there is contribution from the j minus 1k. And we know that the j minus 1 has a coefficient of 1 over delta x squared. All of that we know. The one thing that we are not sure is where do we place it into our matrix here? Okay, for a 9 by 9 equation, we can look at this and say, okay, the j minus 1 in our case here is basically a boundary condition, so that is fine. But for the second value, the j minus 1 is actually t11. So we know t11 is basically the first column, okay, because this is multiplied to t11. So that we know. But in this case, how do we know where it is in our Laplacian matrix? We are going to use this particular function that we have written, because this is going to be general in terms of telling us where to put our unknown or where to put our coefficient in our Laplacian matrix. So my question to you is, if I'm writing my function handled this way, what should the two input be here for the point on the left-hand side? It should be straightforward.
J minus 1 and k.
Yep, j minus 1 and k. Okay, because whatever j is, as long as it is greater than 2, once you call this function where you input j minus 1 and k, it will place it at the point that it is supposed to be in your column vector or in your Laplacian matrix here. Okay. So if you call this, then your I at the left-hand side will be given by this. This will actually give you a number. So from here, you can basically write you can basically place your coefficient in the proper place in your Laplacian matrix. So L is your Laplacian matrix. So here we are going to have I left-hand side. It's the column, not the row. So the row, every row that we have correspond to the each of the j and k point that we collocate is the column that we want to place it in. Okay. So for example, the first stencil is at column 1. The second stencil is at column 2. What we want to do is find out which column to place our coefficient. So in our case, our row is going to be fixed. So our row will always be, let's say I call something else. I call this IN. Let's make things simple. Let's call this NN. So IN would just be NN, J, and K. Okay. So this would be NN, J minus 1K. So here we will always place it at this particular row. Okay. So the column that we want is the ILHS, which is the left-hand side. So this will be your 1 over delta x squared. Okay. So this is your if statement for all the points that has no left-hand side boundary condition. Else, what do you have? So if j is greater than 2, the only point where it is not is when j is equals to 2. Okay, so this will be the case when j is equals to 2. So when j is equals to 2, what do we have? When j is equals to 2, you're basically placing a stencil here. So don't refer to this, okay? This is the node numbering. J equals to 2 is here. So when you place a j equals to 2 here, what do you have on the left-hand side? The left-hand side is now a boundary condition. So this is where, when you use your else statement here, you can just call your boundary condition for IN is basically IN plus whatever value of that boundary condition is from your problem. Why do I have BC plus this? Because boundary condition, they are accumulative. For every row, whatever boundary condition, you're going to sum them up. So this will account for all the summation of the boundary condition value plus this current point. Okay, then we put an N. Okay, so this, you can see the point of me showing you this is to show you how you can actually apply where the left hand, how you can actually call this grid function to figure out where you are going to place your column, the coefficient in your column vector. Okay, as I've said, the row will always correspond to the stencil at JK, which is what we have done here. So this will always be IN. It's the column here that changes depending on which point it is. So this sets up the left-hand side, or the J minus 1. It helps you determine whether the left-hand side point of your stencil is a boundary condition or not. If you put an N and an N here, you are going to be wrong, because this short code only accounts for the j minus 1. You haven't accounted for j plus 1. You haven't accounted for the top part. You haven't accounted for the bottom part. So when you're done with this, you need to write 3 more if statements that will account for these 3 points. Okay. Actually have them here. I have them here actually. But never mind. Let's go back to this. So this, as I've said, account only for the left-hand side. So right now, if I ask, do we have time? We have 10 minutes. If I say, okay, let's continue this on in this slide. Right now, we want to check for the boundary condition on the right-hand side. Okay. So in the if statement before we have done this, now we want to check for this. For the same stencil, is the point on the right a boundary condition or not? What would be your if statement? If you can annotate, feel free to annotate. If you want, you can verbally answer me as well. How do you check if the point here is going to be a boundary condition or not? Okay. Yes, so if j is going to be less than nx, okay, so I'm gonna write it, nx minus 1, then what we are doing is, if j is nx minus 1, where's the thing? Yep. So, okay, let me just clear that one if you don't mind. So when j is nx minus 1, it means that we are looking at 1 point before the last point. So we are actually looking at this point and this point over here. Okay, so for j at nx less for nx less than 1, so that was correct. J less than nx minus 1. What do you have? You will know that the point on the right hand side is not going to be a boundary condition, because nx minus 1 is basically this point and applying a stencil at this point. Okay, so the point on the right hand side, so when you apply it to the first point, the point on the right hand side is actually point 2. So point 2 is not a boundary condition. Okay, same thing when you apply your your stencil to this point, the point on the right is not going to be a boundary condition. So if you write an if statement like this, you know that the point on the right hand side is not going to be a boundary condition, which means that it needs to be put into the Laplacian matrix. So right now you will have your, let's say, I right hand side. It will now call the same thing. So this I'll just tell it to you. So what will be this? It will be j plus 1 k. Okay, so this will not have boundary condition on j plus 1. So j plus 1 has contribution into your Laplacian matrix. So here you have your Laplacian, you have your IN, and then you have your IRHS, then you have whatever you have here. Okay, else you are going to have one boundary condition on the right hand side, because if j is equals to nx minus 1, you're actually placing your stencil here. So the point at j plus 1 is a boundary condition. So what you have is you have boundary condition in is equals to boundary condition in plus whatever value from your boundary condition. So this if statement takes care of the j plus 1. Now you just need to do the same thing for your k minus 1 and your k plus 1. So effectively, within your 2 for loops, you will have 4 if statement. Okay, so this will help you account for the point on the j minus 1, j plus 1, k minus 1, and k plus 1. Don't forget, you still have your j and k term. Okay, you still have your j and k term, which I have not written here, but I think in the Matlab code down there, it's somewhere here. Yep. So you always have your main diagonal of in and in. Okay, so diagonal will always exist, which means that you don't have to check for it. There is no need for an if statement. Okay, every time you place a stencil, the center point will always be an unknown. So you just need to write it directly before your if statement. Okay, so I'm not going to show it for the bottom and the top. Go and try it yourself. well, in fact, you have to do it because in lab 6, there's a problem on 2D FDM. Okay, any questions?
No, sir.
Thank you. What about the others? Make sure you understand this this concept here, okay? It's important. All right. If you have no questions, before I end, I just want to say we have 2 public holidays coming up tomorrow, and not tomorrow, Thursday and Friday, which means again we are going to lose the computer lab. Tutorial is not that critical, so I think because we are basically done with 2D FDM. I think I'll mention this like before again tomorrow before the course. But basically, we're done with 2D FDM. The next part would actually be on weighted residual method and finite element method. So I don't want to start this week. I'm going to start this next week, which means for tomorrow's 9 o'clock class, perhaps I'll use that as a computer lab session. I know it's going to be 1 hour, but I'll try to cover as much as possible. For those who couldn't attend the 4 o'clock session, because historically when I asked them to ask you guys to attend, probably like 3 or 4 only show up for Wednesday's class. Okay, so tomorrow's class I'll do a bit of lab. I was also mention something about this, especially on the elliptic PDE. Okay, because what you have done here is for 2D heat equation, but we should also learn how to solve it for 2-dimensional PDE like elliptic PDE. But as I said, if you can do this, it's just a simple extension to this. Okay. All right. Any questions? All right. If no questions, then